Before going back to the slides, I would like to just show you what happens when you do these forgetting factors stuff. So I'll just read the data from the VEX. To reduce the calculation time, I will just do it to find the daily averages of the temperature and the heat consumption. Also convert the dates, blah, blah, blah. And then I should just change the parameters here. So that is the daily temperature and the daily heat consumption. So, and if we add the temperature on top with the optimal scaling, it looks kind of like this. So it's very easy to see that they are actually doing the same thing. So those are the temperatures using the right-hand axis and the heat consumption using the left-hand axis. So it's a pretty good correspondence. I've made some functions and I'll share the code later for doing the recursive least squares in here. I've done it with the last formulation using P and not R. So I've not done it in this way. I've done it in the last way that I mentioned to make sure that it's robust. You can look into the code if you like. So for a given lambda, I just have the response as my heat consumption. My input is a column of ones and a column of the temperatures to do the linear regression model. And then I just use a lambda of 0.9. And then what I get out are, you can say, what are the input that I get here? What is the prediction error? What is the estimate of theta? And as you know, I cannot do much with the first observation. I need at least 2 observations before I can get an estimate. So I have an estimated intercept and slope here initially. And if I just run through this, plot the errors, I'll zoom in a moment. Intercept of slope. Then you can see pretty much the same plot as I showed you in the slides. The slide we just made on hourly data. But you can see that the intercept, the base load increases when it becomes winter, and the dependence on the outdoor temperature is also being more pronounced during the winter than during, you can say, warmer days. I still have some drops here, and if you look at the errors up here, you also have some large prediction errors, and that's what drives the whole thing. If you look at the error, most of the errors are between minus 100 and 100, and all of a sudden you have 300 some. It just gets away somehow. Now, finding the optimal lambda, basically what we want to do is to run the algorithm and make a sum of the squared prediction errors excluding the first observations. So I exclude the first 50 out of those 365 days. Pretty much exclude most of the summertime, and that's also fair because we don't care about it as such. What I will do is just to evaluate it for a sequence of different lambdas, run the algorithm for all of these, and plot what it looks like. And, well, I think I need to do one thing. So basically what you see here is the optimal values of the order of 0.8. Why not find the optimal value by optimizing? It's very close to 0.8, 0.79. And then we should run the algorithm with that and show a similar plot to the one before. We still have something happening here at around day 210. So something happens. We get one large negative residual here of minus almost 600 in this case. What happens there? I don't know. But let's look at those that are negative, very large negative residuals at the date of the data, of the incoming data, and they are row 210 and 211. That's where we have large negative residuals. So let's just show you the neighboring observations. So we have temperatures in this period that are -3 degrees roughly as a daily average those days. But then those particular days here, maybe also including the one before, in particular on day 210, that's the one day with the very large error, you're using 200 units more of heat than on the day before and the day after that have the same temperature. 10% larger consumption, but same temperatures. Something is odd there. And if you look at the neighboring days, you're even down to 1600, 1800 with similar temperatures. And given the estimated slope here is of the order of 60 per degree, 60 units of energy per degree, then you can say all these here should not differ that much. The 1600 is kind of what is expected at these temperatures. 1600 down there, 2 degrees, so you should only expect 1700. So all of a sudden we have some very large consumption during some few days. I don't know what happened there, but that is what happens. But that is also what is driving the optimal lambda. Because all of a sudden what matters the most is how do you forget that observation? So you could want to consider, I will ignore this observation, but not for now. We can also do this on an hourly basis. It does pretty much the same thing. The only difference is the calculation time is a little bit longer to evaluate for a different number of values. And what we see is that we should use something that has a smaller lambda, so we should forget much faster to do the optimal 1 hour prediction. And the optimal value in this case is roughly 0.5. So it roughly means just use the last 2 observations to predict the next one. Now, why is this a good choice? Let us look again using the optimal value and do the same plot as before. When we look at the hourly data, everything becomes more messy. We have still some large residuals here in the middle. But basically what happens here is that we pretty much use the prediction to be the most recent observation. So we have a lot of noise in this system, so it's not a good estimator. It's just the optimal one-step prediction estimator is to use the most recent past. This is one of the cases where effectively, if you're running a district heating network, you do not care, well, you do care about the one-step prediction, but you care more about the 6 to 8 hour prediction, maybe 10 hour prediction, because that's the heat consumption in 10 hours, that is what you need to send out to the pipes now, because that's time lag shifting water around. If we do it with variable forgetting, I set a default minimum value for lambda of 0.5. The rest is just implementing the function. If I run this, and plot, I get something like this on the daily data. It behaves quite nicely. What we should look at is what is then actually the lambda that we used. Looks like this. So what is this? What is happening here? We can easily identify the observation 210 there. It pretty much says, forget everything you can, and then start remembering again. So what happens is, whenever you have a large residual, it just forgets what happened and then relearns. It does work quite effectively, and in practice it also does work, but you have this memory that is oscillating quite a bit up and down. You can do things, you can do other implementations that give you a more stable memory, but it's still flexible memory. So the memory, basically something along the lines of an exponential smoothing of the memory. So you don't have those dips that are that hard, where you kind of forget everything. But now, what is the average memory here? The optimal for the daily data was to use 0.8. The average is 0.95. So it means that since we have to say 1 divided by 1 minus lambda, we have on average 4 times more memory here. And out of the 366 observations, only 16 are below the optimal fixed lambda. And of course, now I did not tune this, and I can run the same thing on the hourly data. I just, of course, have to use, I picked a representative penalty value out here corresponding to what was the optimal lambda before. If I go back here I have 5 times 10 to the 7th, but I actually go with something that is much smaller to force it to be flexible. And the predictions here, well, they look, if you compare with before where I used the 0.5 as fixed memory, where everything was just pretty much noise, right? Do you recall it, or should I go back? You can see here it actually behaves quite a nice, in the sense that it behaves sort of like the daily model, where you have this increase in intercept during the winter time and then decrease again. We still have something happening here in the middle. We also see that the slope kind of does something. But if we look at the lambdas here, over time, they don't get down to the minimum. They get down to 0.65, but they generally stay up there. But you have a lot of small spikes coming down. Many hours where you forget something. But also many hours where you don't forget anything, because the average is 0.98. And if you just look at the interval in the middle, where things are really shaky, or just look at the small period, what happens is that every now and again you forget. Every day or every other day you forget some, but you don't get down to very low values. Whereas the optimal 1 hour is 0.5. So when we do it adaptively here, we can get something that we actually keep much more memory in the system, but you can still run it. So don't have a fixed lambda unless your system is robust to that. Okay, so that was what I wanted. And maybe I should just add that to slides before showing it again, so I don't get that surprise, so to speak. The next, and I would say probably last element related to the linear part here is, well, another way of doing this. If you look at this model instead, I hope you can recognize this as a Kalman filter setup. The one thing that is different from what we usually do is that there's no A there, which means that we just say that the states up here are just random walks. So we have a system of states that are just random walks. They're not connected at all. They're just independent random walks with some noise that may have some correlation structure. And then we observe it through something where we say that the CT matrix here depends on time. So what is this model actually capable of doing? What if I have CT as a 1 and a temperature corresponding to the time t? So I'll update CT to be a row vector with a 1 and a temperature. If I do that, what will this model actually reflect? Yes? It's a linear model with random walk processes for the parameters. Now, if you run the Kalman filter, what it will do is to use, similar to what we have over here, the one-step prediction errors to update those parameter values. So this is a different way of doing a recursive, adaptive estimation of a model. So why then use the Kalman filter? And instead of doing this, not in this way, but the recursive version of this, what is the advantage of doing the Kalman filter as opposed to what we did, say, here? What is the big difference? The big difference is that when you do things adaptive with a fixed lambda or variable lambda, basically what you say is that all parameters have the same memory. Here you can say by tuning sigma 1, the diagonal elements in that, you can say that, say, the intercept has one memory, whereas the slope has a different memory. So you can pick different variances for the different parts, and thereby you can make the model here more adaptive in some parameters than in others. You can actually almost fix parameters if you like, which you cannot do in the other sense. That's one part. The other part is, well, you can of course also extend this to say the parameters may not be random walks. It could be that you want an ARIMA structure for one of the parameters for whatever reason. Could make good sense to say that it's not fully random walk. It's something that is not, has more structure to it. So this is much more flexible. One more thing. This algorithm here is made to work, so if you have no missing observations. In practice, you always have some missing, something that is behaving odd somewhere, at least in most settings. Of course, you can do that in this setting without doing the update, but then you have to kind of add that into the algorithm. It's not there by default. But in the Kalman filter setting, it just goes across. We saw that last week. We discussed this. That's basically the same thing, just formulating as parameter vectors here. So we'll skip that. And well, what can we do? We can also have ARMA models where we have parameters that are time varying in this sense, because we allow the parameters to drift. We can also have, you can say, yeah, the parameters to follow functions of time or whatever we like to. When we have, if we have an ARMA model where that's a stochastic process, but the parameters are also stochastic processes, then we label that as a double stochastic process, because you kind of have two layers of stochasticity. And yeah, in all those cases here, you can use a Kalman filter to kind of trace that and estimate things. So that's where I see everything from pretty much throughout the entire course ends up with one answer. It's not always the easiest answer, but it's the one answer that can always be an answer. Pretty much. So for the next part, I will say a little bit about what next. I hope you can see that this is not a linear process. So there are, I don't know how many of you know chaos theory, and it's kind of the traditional quote is saying, well, if the linear world is represented by elephants, then the nonlinear world are non-elephants. And that's basically the same here. We do a lot of things in the linear world because it's easy, and we try to make linear approximations of everything, but in reality, most things are nonlinear and connected somehow. But still, the linear approximation, if we do things adaptively and so forth, we can accommodate many things, but again, be careful out there. So this process is a so-called stochastic differential equation in continuous time. Of course, as I said many times, I cannot make that plot in continuous time. I have to sample it. But what we have here is what is called Brownian motion. It's basically a random walk in continuous time. Comment back on that in a moment. And the process is basically, it's a differential equation here, stochastic differential equation as mentioned. The term here says that this term, if xt is close to -1, this becomes small. If you're close to 1, this becomes small. And minus here in front means I drag you towards the center. And that is what happens. You're living around -1. At some point, you get too close to the center, and you swap to the other side. And then you stay there for a random period of time until you swap again. That is what happens in this process. Now, the random walk Brownian motion here in continuous time has some, when you just look at it, it looks just like a random walk. And as such, the simulation, when it's observed in discrete time, is the same thing. But just showing some different things, it's similar to plot you would make for random walks. But there are differences. It is continuous with probability 1. So a random walk, you have jumps, but a Brownian motion is continuous. Consider an atom or a gas particle flying around in air. That's kind of a typical representation of Brownian motion. And it's nowhere differentiable. Again, with probability 1. That's not a fun function to evaluate. Now, the other thing is, pick any time interval. It's a continuous curve. So why don't you just strengthen it out? It continues forever. Because it's nowhere differentiable. It continues. It has infinite length, even for any small time interval. You can always subdivide and subdivide and subdivide and subdivide. So it has some quite different properties from what you're used to. I don't know if you've met curves that kind of fit in a small area that has infinite length before. Some of you may have that, even back in high school. A classical one. If I do this, take this line, divide it into 3, and take the middle section and do like this. And then I continue with that operation. What do you call this? And now at some point here, my lack of precision, I can maybe try to do one more iteration on this. But if I continue this part here, what is the length of this line that I'm drawing? Just say something, I'm listening. This is a tough one. Anyone? What is the length going to be of this line when I continue this a few more iterations? Oof, I was doing that part. Anyone heard of fractals before? This is what it becomes in a moment. if I could continue to infinity. I'm not that good at drawing infinite many lines here, but it's the same thing that actually happens to some extent. I wish I was faster at doing this, but I'm almost there, so I will finish this iteration. And then you take each of these lines and you subdivide that into 3 pieces and do the same. So this is an infinite line if you're stretching it out, if you've done it recursively enough. It has fractal dimension 4/3. Anyways, so in the 4/3 dimensional world, it's finite. That means in the 2-dimensional world, it stays within a small area. Anyways, but this process here, it's not like a fractal, even though it's to some degree similar. Because in the infinite setting, this function is also not differentiable anywhere. Because every element will be subdivided everywhere. So you have some properties here. And that's basically, when you look at, that's the equation from before, stochastic differential equation. In more general, well, you have a drift term here, where is the process driving you, and you have a diffusion term here as to how are things spreading out, how are things being smoothed out. That's how you kind of look at it. And it is effectively an integral equation where the last bit here is a stochastic integral. So, but here you can have nonlinear functions, you can have anything. It's just that the distributional things are becoming more and more complex, wherever you go. So that's one topic. Another topic is cointegration. It's quite common in financial theory. Basically, many financial processes are non-stationary. So when you have 2 processes that are non-stationary of order 1, meaning that if you do one lag differencing, then it's stationary. You can also call them unit root processes, and there are other terms for that. If you can make a linear, so these are 2 processes, if you can make a linear combination of the 2, like here you have x2 minus 1 minus 2 times x1, and then you get something that is stationary. Then the original 2 processes are co-integrated. Because you get difference of them is a process that we can model as stationary. So it's just a different representation of this. Here are some links you can look at, and I can just say that doing this is enough to get the Nobel Prize. But you have to be the first one to do it. But it means that you can actually also get it by doing something time series analysis. So you have to find your own niche and do it right. That's always good. And you can say one thing that we have kind of strained ourselves to a state space that is typically a few states. But in practice, things are also have a spatial, or some things have a spatial dimension that you cannot just lump into, say, what is the average temperature of this, not house, but city or whatever. So you can have spatial structures. One could be the chlorophyll concentration in oceans, that some of us is going to spend some more time on. How to use satellite imaging to see the concentration, how to model that to get a spatial component, not just where you go out. I don't know if you've seen the news recently about measurements of water quality, that the reference laboratory going to assess the measurements in Denmark, they used the wrong test method. So that's wrong. Now what do we do? What we could do, and what we are working on, not because of that, but as a separate process is to use satellite imaging from the Sentinel mission to actually assess what is going on. Because you can look at the color. If you have a sand bed and you don't have too much water, then you can look at the color of the water and see what is actually growing there. Do you have a lot of algae and things growing or not? Anyways, that's just an example. Sunspots. And then if you just want a lot of data to play with and don't know what to do with your time, I don't expect that. So the easy say, what is the next course would be advanced time series. That's a lot of all the nonlinear methods, taking pretty much everything that we looked at and try to do that in a nonlinear dimension as well. Take the so-called extended Kalman filter, where you don't just have a times x, but you can have a function of x and a lot of other things. So that means you can have nonlinear relationships between your states, which is happening quite often. It's actually quite restrictive for me to say, well, what can I actually model within the scope of elephants? Because pretty much all I do is in the non-elephant world. If you want to know more about stochastic differential equations, 02425, diffusions and stochastic differential equations is, you can say that's where you get the sound basis also for how to do the analytical part, but also the numerical simulation part. And the stochastic processes course is, you can say, a complementary thing to this. I don't know if any of you took it, but where we are living in a continuous state space, what happens there is you more look at when you jump between discrete states. The classical example there is, I don't know how much you know about insurance and financial credit risk and stuff like that, but what you want to have in that world is to have a AAA rating, and if you have that, that's the best rating. That means you can get loans at a good price. Whereas you go down to a B rating or C rating or D rating, at some point you're not going to get that loan because your credit score is just too low. But how do you model the process, jumping between what is the likelihood that a AAA country becomes a B? So what is how much risk do you want to run? Stuff like that. And of course, there are many more courses out there that have, you can say, relevant contributions where knowledge of time series could be taken into account. So I think today the most important thing is first just to do the setup for adaptive recursive least squares, but also to recognize that it's not too different from the Kalman filter, and that we can use that for, say, tracing parameters as one thing, but for many other things. And also, well, if you're going to continuous time, if you have nonlinear systems, if you want to do it with stochastic differential equations, where to go. Also, one more thing, just to reflect backwards in time, we're doing that the last couple of weeks. When we go from a continuous time description of a system to a discrete time system, we generally have more parameters. That also means we have more parameters to estimate. So often it's nicer to do things in a continuous time description, even though you have discrete time observations. I think that was what I wanted to say, besides this one. I did not make this one, but it was a colleague of mine. Last year, I think it was. Any questions?